Hello and welcome to another video of control engineering. Today we will look various aspects of transfer function. In the last videos we have seen Laplace transform of differential equations. So today we will see how we can use that in control engineering. So to start with, we will look into the first problem. Find the Laplace transform represented by differential equation shown below, dc of t by dt plus 2c of t equal to r of t. Taking Laplace transform on both sides, assuming zero initial conditions, we will get dc of t by dt, where c of t is the output, equals s into c of s. C of s is the Laplace transform corresponding to c of t, plus 2c of s. C of s is Laplace transform corresponding to c of t, equal to r of s. Now, the definition of transfer function is, it is the ratio of the Laplace transform of the output to the Laplace transform of the input for all initial conditions equal to 0. So initial conditions are 0. It is generally represented as a block diagram with input on the left and the output on the right, and the system transfer function inside the block diagram. R of s is the input, G of s is the transfer function, C of s is the output. So G of s is nothing but the ratio of the Laplace transform of the output to the Laplace transform of the input. So here in this problem we have s plus 2c of s equal to r of s. So c of s by r of s will be equal to 1 by s plus 2. So 1 by s plus 2 is the Laplace transform of the differential equation represented by this equation. In the second problem, find the unit step response for the above system, a system with a transfer function 1 by s plus 2, assuming zero initial conditions. So g of s is the transfer function. It is 1 by s plus 2, that is equal to c of s by r of s. Now r of s is unit step function, and they have asked us to find what is c of s. C of s is the output. So find the response c of s for a unit step input. So to get c of s, we will take this to the other side, r of s into g of s. You have r of s for a unit step, the Laplace transform is 1 by s, and g of s is 1 by s plus 2. Using partial fraction expansion, we will get k1 by s plus k2 by s plus 2. When we calculate the value of k1 and k2, we will get k1 as 1 by 2 and k2 as minus 1 by 2. How to calculate this we have seen in the previous videos. So here we will get 1 by 2 by s and minus 1 by 2 by s plus 2. So the inverse Laplace, taking the inverse Laplace of transformed function is, so this is the inverse Laplace of this function. So that is nothing but inverse of c of s will be c of t equals 1 by 2 minus 1 by 2 e raised to minus 2t. So in the time domain, it is this is the step response, unit step response for that system. So in this second problem, what we have seen is, we will give a unit step input to the transfer function g of s, and we will calculate the Laplace transform, and we will find the inverse Laplace transform. So that is the response, the unit step response of this system. So c of t is what we have calculated here. In the third problem, the same as it is similar to second problem, except that the input that we are giving now is e raised to minus t. So we would like to get the response c of t of the system, the same system, 1 by s plus 2, when we give r of t equal to e raised to minus t. So similarly, the same way we can calculate c of s is equal to r of s into g of s. Now using partial fraction expansion, we have split it into a by s plus 1 plus b by s plus 2. After calculating a and b values, we will get 1 by s plus 1 minus 1 by s plus 2. Taking the inverse Laplace, you will get e raised to minus t minus e raised to minus 2t. So this is the time domain representation of a unit step, for a input of e raised to minus t for the system 1 by s plus 2. So 1 by s plus 2 is the system, r of s is our input and c of s is the output. So suppose you are giving r of t as e raised to minus t, converted it into frequency domain, and then multiply it with our transfer function to get c of s. Then you will find the inverse Laplace c of t. And another application of Laplace transform is, if suppose a differential equation like this is given, we can find the corresponding transfer function. Transfer function is the relation between input variable and the output variable. So what is the transfer function? G of s equal to y of s divided by r of s. So to find that, we will take Laplace on both sides, on the input side, on the output side, and the input side. So on both sides of the equation, we'll take the Laplace transform. So this, so taking the Laplace transform of d cube y, you get s cube y of s, and d square y, you will get s square 3s square y of s, 7s y of s, and 5 y of s. You are taking y of s as common, and in the right hand side you have d square s square r of s, 4s r of s plus 3 r of s. And to get the ratio y of s by r of s, you'll take this on the other side and this side. So it will be s square plus 4s plus 3 divided by s cube plus 3s square plus 7s plus 5. So this is how a Laplace transform is used to get the transfer function from a differential equation. So you will be given a differential equation. So this can be further used in many ways. If suppose you are giving some input like unit step or e raised to minus t, what is the response? How to calculate y of s? So that are the further steps after calculating this transfer function. So these are the few applications of transfer function. Thank you.